4,500 years ago, structures were built in the deserts of Egypt with a precision that surpasses modern skyscrapers. The pyramids were built with an accuracy of 2 centimeters, and traces of machine processing have been found in ancient sarcophagi. How did a Bronze Age civilization possess laser-like precision technology? Today, we will reveal the secrets of lost knowledge that are forcing us to rewrite human history. Get ready for a journey into a world of technology that was thousands of years ahead of its time. If the mysteries of ancient civilizations make you wonder about the limits of human capabilities, subscribe to the channel and like the video. In the comments, let's discuss a controversial question. Could the ancient Egyptians have obtained their knowledge from a more advanced civilization? Or is it all the result of centuries of accumulated experience? When British surveyor John Hershey Cole took the first accurate measurements of the Pyramid of Cheops in 1925, the results shocked the scientific community. The base of the greatest pyramid in Giza deviates from a perfect square by only 2 centimeters. For comparison, in the construction of modern skyscrapers, an error of several tens of centimeters is allowed. How did the ancient Egyptians achieve such incredible accuracy 4,500 years ago? The Pyramid of Cheops is oriented to the cardinal points with a deviation of only 3 angular minutes, which is the accuracy of modern laser theodolites. The north face deviates from true north by 2 angular minutes and 38 seconds, which is an error of less than 1/100%. Such accuracy requires knowledge of true north, not magnetic north, since the magnetic declination in the Giza area is about 2 degrees. The height of the pyramid, 146.6 meters, corresponds to the perimeter of the base exactly as the radius of a circle corresponds to its circumference. This means that the ancient builders knew the number pi to 5 decimal places. Official science believes that pi was discovered by ancient Greek mathematicians who lived 2,000 years after the builders of the pyramids. The pyramid blocks are fitted together with millimeter precision. It is impossible to insert a razor blade between the granite blocks in the king's chamber. At the same time, each block weighs up to 15 tons. Modern builders working with such masses are satisfied with an accuracy of a few centimeters. Analysis of the limestone blocks showed that they were cut using tools that left marks characteristic of modern diamond saws. The scratches on the surface of the stone are of equal depth and parallel to each other with micron precision. Such marks cannot be left by copper tools, which, according to official history, were used by the ancient Egyptians. Granite blocks with perfectly flat surfaces have been found in the underground chambers of the pyramid. The deviation from the plane does not exceed 2/100ths of a millimeter over an area of several square meters. Such precision can only be achieved with modern numerically controlled grinding machines. The angles of the inner chambers are accurate to the angle seconds. The rectangularity was checked with modern laser measuring instruments. No errors were found. This means that ancient builders had angle measuring instruments that were more accurate than most modern ones. The ventilation shafts of the pyramid have a cross-section calculated with mathematical precision to ensure optimal air exchange. The angles of the shafts correspond to the positions of certain stars in the sky at the time of the pyramid's construction. This requires knowledge not only of architecture, but also of astronomy and aerodynamics. The mystery of the pyramid's accuracy forces us to rethink our ideas about the technological capabilities of ancient civilizations and ask ourselves, what knowledge and tools have been lost to humanity? In 1995, American engineer Christopher Dunn examined the granite sarcophagus in the king's chamber of the Pyramid of Cheops and discovered traces that overturned ideas about the technology of ancient Egypt. On the inner walls of the sarcophagus, parallel scratches characteristic of modern machine processing are clearly visible. The distance between the scratches is exactly 3 millimeters. Such uniformity cannot be achieved by hand. Microscopic analysis showed that the scratches are all the same depth, 0.2 of a millimeter, and perfectly parallel to each other. This indicates the use of a cutting tool that moved at a constant speed and under constant pressure. Modern milling machines leave exactly such marks when processing granite. Granite blocks with holes drilled 10 centimeters in diameter and up to 1 meter deep were found in the temple at Abydos. The walls of the holes are perfectly smooth, and concentric drill marks are visible at the bottom. The penetration rate into the granite was 2.5 millimeters per drill rotation, which exceeds the capabilities of modern diamond drill bits. Petrie discovered a core in Giza, a cylindrical sample of granite extracted during drilling. Spiral grooves with a pitch of 1 millimeter are visible on its surface. Such marks are left only by modern drilling rigs with diamond bits operating under high pressure and with forced cooling. In Serapeum, an underground complex in Saqqara, there are 24 granite sarcophagi, weighing 70 tons each. The inner surfaces of the sarcophagi are finished with a precision unattainable with hand tools. The deviation from the plane does not exceed 0.05 of a millimeter, and the angles are accurate to the minute. The lids of the sarcophagi and serapeum fit so precisely to the bases that it is impossible to insert a human hair between them. At the same time, the contact area is several square meters. Such precision can only be achieved with modern coordinate measuring machines and numerically controlled machine tools. Traces of sawing are visible on the surface of some sarcophagi. Parallel scratches a fraction of a millimeter deep, spaced at equal intervals. Analysis showed that the saw moved at a speed of about 30 meters per minute and penetrated the granite to a depth of up to 2 millimeters with each pass. The Cairo Museum houses diorite vases from the era of Pharaoh Khasehemu, who lived 5,000 years ago. The walls of the vases are less than a millimeter thick, and the necks are so narrow that it is impossible to insert a finger inside. At the same time, the inner surface is perfectly polished. The creation of such items requires the use of high-speed spindles and diamond tools. Research by Japanese scientists using X-ray tomography has shown that some statues have complex internal cavities that are inaccessible to manual processing. This indicates the use of three-dimensional milling technologies, which only appeared in modern industry in the 20th century. Traces of machine processing in Egyptian artifacts cast doubt on the official version of primitive technologies in ancient times and force us to look for explanations for these archaeological anomalies. One of the greatest mysteries of ancient Egypt is the transportation of megaliths weighing hundreds of tons over distances of thousands of kilometers. Granite obelisks were delivered from the quarries of Aswan to Luxor, a distance of 200 kilometers along the Nile. Some of the monoliths weighed more than 300 tons. Modern cranes are only capable of lifting such loads using special technology. The unfinished obelisk in Aswan is 41 meters long and has an estimated weight of about 1,200 tons. It was cut from a solid rock, but remained in the quarry due to a crack. This colossus was supposed to be the largest obelisk in human history. Modern cranes are not capable of lifting loads of this weight. Special equipment is required. The Memnon statues in Luxor weigh 750 tons each and are carved from solid blocks of quartzite. This material was mined in quarries near modern-day Cairo, which means it had to be transported over a distance of 700 kilometers. Quartzite is one of the hardest natural stones and requires diamond tools to cut. The temple at Baalbek contains 3 megaliths weighing 800 tons each, known as the trilithon. These blocks were raised to a height of 7 meters and are perfectly aligned with each other. In a quarry near the temple lies another block weighing 1,200 tons, which was never used in the construction. Research by engineer Michael Heiser has shown that lifting mechanisms with a capacity of at least 2,000 tons would have been required to transport the trilithon blocks. Such cranes only appeared in the second half of the 20th century. Moreover, the ancient builders not only lifted these blocks, but also installed them with millimeter precision. The granite blocks in the king's chamber of the Pyramid of Cheops weigh between 15 and 80 tons each. They were lifted to a height of 50 meters and installed in the narrow passages of the pyramid. Some of the corridors are only 1 meter 20 centimeters wide, making maneuvering such loads an extremely difficult task. In Abu Simbel, there are 2 temples carved entirely out of rock. The facades are decorated with statues up to 20 meters high, carved from a single mountain. In the 1960s, the entire complex was cut into blocks and moved to a new location due to the construction of the Aswan Dam. Modern technology made this operation possible, but how did the ancient Egyptians create such structures? Transporting the blocks of the Pyramid of Cheops required moving 2,300,000 stone blocks, weighing a total of 6 million tons. During the 20 years of construction, 315 blocks were laid every day. This means that 1 block was installed every 2.5 minutes during a 10-hour working day. Traces of heavy loads being dragged have been found on the roads between the quarries and construction sites. The ruts are up to half a meter deep, indicating the use of carts or sleds of enormous weight. However, there are no traces of wheels. The ancient Egyptians preferred sliding surfaces. The methods used to transport megaliths remain one of the main mysteries of ancient Egyptian civilization, suggesting the existence of lost technologies for lifting and moving super-heavy loads. In Egyptian temples and pyramids, archaeologists have discovered holes in granite that baffle modern engineers. These perfectly round holes are drilled into the hardest stone with the precision of modern drilling rigs. British archaeologist Flinders Petrie was the first to notice these anomalies in the late 19th century and claimed that the ancient Egyptians possessed drilling technologies that surpassed the capabilities of his era. In the temple at Karnak, a hole 8 centimeters in diameter and more than a meter deep was discovered, drilled at an angle into a granite block. The walls of the hole are perfectly smooth, without chips or irregularities. At the bottom, concentric grooves characteristic of rotary drilling are visible. Modern diamond drill bits leave exactly the same marks. Kerner, a cylindrical sample of granite found by Petrie in Giza, became one of the most mysterious artifacts of ancient Egypt. Its surface shows spiral grooves a fraction of a millimeter deep, spaced at equal intervals of 1 millimeter. This spiral pitch indicates a drill feed rate 500 times greater than that of modern machines working with granite. Analysis of the grooves on the core showed that the ancient drill penetrated the granite to a depth of 2.5 millimeters per revolution. Modern diamond drill bits penetrate granite to a depth of no more than 0.05 of a millimeter per revolution. This means that ancient drills were 50 times more efficient than modern ones. Holes up to 15 centimeters in diameter and more than 2 meters deep have been found in Abydos. Some holes have a complex shape, widening inside the block to form internal chambers. Creating such cavities requires the use of special expanding drills or ultrasonic drilling technologies. The tubular drills used by the ancient Egyptians left characteristic marks in the stone. Longitudinal scratches are visible inside the holes, and the cores have grooves on the outer surface. This indicates the use of hollow drills with cutting edges at the end. The principle of operation corresponds exactly to modern column drilling technology. Holes drilled in diorite blocks, a rock similar in hardness to granite, have been found in the Temple of Horus in Edfu. The diameter of the holes varies from 2 to 20 centimeters, and the depth reaches 1.5 meters. All holes are perfectly cylindrical in shape and have smooth walls. The drilling speed of ancient craftsmen amazes modern engineers. To create a hole 10 centimeters in diameter and 1 meter deep in granite, a modern diamond-tipped drill takes about 8 hours. Analysis of traces in Egyptian temples shows that ancient craftsmen performed such work much faster. Some holes in Egyptian monuments are conical in shape, widening towards the surface of the stone. This is characteristic of modern countersinking technology, where the hole is machined with a special tool to create a chamfer, or seating for fasteners. Holes have been found in the Pyramid of Cheops that were drilled through both sides of a granite block and precisely aligned in the center. The alignment error does not exceed 1 millimeter with a block thickness of 1.5 meters. Such precision requires the use of laser guidance systems. The granite drilling techniques used by the ancient Egyptians remain a mystery to modern science and engineering. The metallurgical achievements of ancient Egypt amaze modern scientists with their complexity and perfection. Analysis of Egyptian metalwork shows the use of technologies that were thought to have been invented much later. An iron dagger made of meteorite iron with a nickel content of 8%, a composition characteristic of space objects, was found in Tutankhamun's tomb. Chemical analysis of Tutankhamun's dagger showed no corrosion after 3,300 years in the tomb. Modern science explains this by the high nickel content. But the technology for processing meteorite iron requires temperatures of over 1,500 degrees Celsius and knowledge of complex metallurgical processes. Copper pipes up to 30 centimeters in diameter and over 10 meters long have been found in Egyptian temples. The walls of the pipes are 2 millimeters thick throughout, indicating the use of rolling or drawing technologies. Such methods of copper processing did not appear in Europe until the Middle Ages. Gold artifacts from the tombs of the pharaohs demonstrate a mastery of techniques that modern jewelers consider the pinnacle of craftsmanship. Tutankhamun's gold mask weighs 11 kilograms and is made from a single sheet of gold 2.5 millimeters thick. The creation of such an artifact requires a deep knowledge of metalworking. Analysis of the gold jewelry revealed the use of granulation, a technique involving soldering tiny gold balls less than 0.5 millimeter in diameter to the base. The melting temperature must be so precise that the solder melts but does not damage the granules. This technology was lost in the Middle Ages and only rediscovered in the 20th century. Bronze alloys with tin, lead, and other metals added in strictly defined proportions were found in the sarcophagi. The composition of some alloys exactly matches modern industrial standards for maximum strength and corrosion resistance. This indicates a deep understanding of the influence of alloying elements on the properties of metal. Silver items from Egyptian tombs contain between 2 and 5% gold impurities. This composition is characteristic of natural electrum, but analysis has shown that the ratio of metals was strictly controlled. This means the use of silver purification and alloying technologies that only appeared in modern metallurgy in the 19th century. Copper statues covered with a thin layer of gold, less than 1 micrometer thick, were found in the Temple of Dendera. Such a coating can only be applied by electroplating or vacuum spraying. Both technologies require knowledge of electrochemistry and were invented in the 19th and 20th centuries. Studies of iron artifacts from the New Kingdom era have shown the use of carbonization technology, saturating the surface of iron with carbon to produce steel. The depth of the carbonized layer ranges from 1 to 3 millimeters, which requires precise control of temperature and processing time. Egyptian craftsmen mastered the technology of casting using meltable models, a method that allows the creation of complex shapes with thin walls and small details. Bronze statuettes with hollow interiors and walls less than a millimeter thick have been found in tombs. The metallurgical achievements of the ancient Egyptians demonstrate a level of knowledge that modern science considered unattainable for that era, forcing us to rethink our ideas about the technological development of ancient civilizations. The optical technologies of ancient Egypt included the creation of lenses, mirrors, and other devices that modern science considers to be achievements of much later eras. Polished crystal lenses up to 5 centimeters in diameter, processed with the precision of modern optics, were found in Tutankhamun's tomb. The surfaces of the lenses are spherical, with a deviation of less than 1/100th of a millimeter. Analysis of the crystal lenses showed that their optical power ranges from 2 to 5 diopters, which corresponds to modern eyeglass lenses for correcting farsightedness. The surfaces are polished to a mirror finish, without the use of modern abrasive materials. Achieving this level of workmanship requires knowledge of the principles of geometric optics. Bronze mirrors with a diameter of up to 30 centimeters and a perfectly flat reflective surface have been found in the Temple of Dendera. The deviation from the plane does not exceed 1 micrometer over an area of several hundred square centimeters. Modern telescopes use mirrors with similar accuracy characteristics. The reliefs in the Dendera temple depict priests holding objects resembling electric lamps. Some researchers interpret these images as evidence of the use of artificial lighting in underground temples. Analysis of soot on the ceilings showed that many rooms were lit not by torches, but by other light sources. Obsidian mirrors with a parabolic surface capable of focusing sunlight to a point less than a millimeter in diameter have been found in Saqqara. The temperature at the focus of such mirrors reaches 1,500 degrees Celsius, enough to melt copper and bronze. This indicates the use of solar energy in metallurgical processes. Egyptian craftsmen created composite mirrors from several segments that were precisely fitted together. A mirror consisting of 7 silver plates, forming a single reflective surface, was found in the tomb of Kentaferes. The seams between the plates are almost invisible, which requires the highest level of metalworking skill. An analysis of hieroglyphic texts contains descriptions of devices for observing the stars, including stones that bring the distant closer. Some researchers interpret these descriptions as references to the use of telescopic devices 2,000 years before their official invention in Europe. Reliefs depicting instruments similar to modern surgical loops have been found in the Temple of Kom Ombo. Nearby are scenes of medical operations using magnifying devices. Edwin Smith's papyrus contains descriptions of surgical procedures requiring precision that would be impossible without optical magnification. Glassware from Egyptian tombs demonstrates mastery of complex glass-making techniques. Glass beads less than a millimeter in diameter, with holes 0.2 of a millimeter in diameter, have been found. The creation of such items requires the use of magnifying devices and precision instruments. Egyptian artists created microscopic images on the surface of precious stones less than a centimeter in size. Scenes with dozens of human figures less than a millimeter tall are carved on seals made of carnelian and jasper. It is impossible to distinguish the details of such images without multiple magnification. Polished granite surfaces in temples were used as astronomical mirrors for observing stars in water. The reflectivity of such surfaces reaches 90%, which is comparable to modern telescopic mirrors. The creation of such surfaces requires knowledge of the principles of light reflection. The optical achievements of the ancient Egyptians testify to their deep understanding of the nature of light and their mastery of technologies that were considered lost for millennia. The medical knowledge of the ancient Egyptians amazes modern doctors with its accuracy and depth of understanding of human anatomy. The Edwin Smith Papyrus, dating from the 17th century BC, contains descriptions of 48 surgical cases with detailed analyses of head, neck, and chest injuries. The accuracy of the anatomical descriptions corresponds to modern medical textbooks. Egyptian doctors performed trepanation of the skull, a complex neurosurgical operation requiring a deep knowledge of brain anatomy. Museums around the world have skulls with perfectly round holes ranging from 2 to 5 centimeters in diameter. The edges of the holes are smoothed, indicating healing after surgery. The patients survived. Analysis of mummies has shown that Egyptian surgeons performed operations on the heart, liver, and other internal organs. Traces of surgical intervention in the chest area were found in the body of the mummy of Pharaoh Ramses II. The incisions were made with the precision of a modern scalpel, and the sutures were made with absorbable threads. The Ebers Papyrus contains descriptions of more than 700 medicines and methods of their use. Many recipes include plants that modern pharmacology recognizes as effective for treating the diseases described. Dosages are indicated with gram precision, which requires an understanding of the principles of pharmacokinetics. Egyptian doctors were skilled in cataract surgery, the removal of the clouded lens of the eye. Reliefs in the Temple of Kom Ombo depict surgical instruments, including devices resembling modern ophthalmic instruments. Eye surgery requires microsurgical precision and knowledge of the anatomy of the visual apparatus. Analysis of mummy teeth has revealed the use of gold and silver dental fillings. In some cases, signs of endodontic treatment have been found, which is the removal of the nerve from the root canal of a tooth. Such operations require an understanding of the structure of the tooth and the use of fine instruments less than a millimeter in diameter. Egyptian embalmers demonstrated a deep knowledge of the biochemistry of tissue decomposition. The composition of embalming mixtures included antiseptics, tanning agents, and preservatives in strictly defined proportions. Modern analysis has shown that these compositions effectively prevent the growth of bacteria and fungi. Bronze and iron surgical instruments have been found in tombs, including scalpels, tweezers, needles, and forceps. The sharpness of the blades was tested using modern methods and found to be comparable to that of modern surgical instruments. Some instruments have complex shapes designed for specific operations. The Kahuna Papyrus is dedicated to gynecology and obstetrics and contains descriptions of methods for determining pregnancy with accuracy down to the week. Egyptian doctors knew about the connection between the menstrual cycle and the possibility of conception, which was considered a discovery of the 20th century. Methods of pain relief during childbirth using herbal preparations are described. X-ray examinations of mummies have revealed traces of complex surgical operations, including tumor removal, bone fracture treatment, and prosthetics. In some cases, metal pins were used to fix bone fragments, a technology that is considered an achievement of modern orthopedics. Egyptian doctors understood the principles of asepsis and antisepsis thousands of years before the discoveries of Lister and Pasteur. Descriptions of surgical preparation include washing hands and instruments with solutions with antiseptic properties. Wounds were treated with honey, which modern medicine recognizes as an effective antibacterial agent. The medical achievements of ancient Egypt testify to the existence of a developed system of medical education and scientific research, the results of which were largely ahead of their time. The astronomical calculations of the ancient Egyptians demonstrate a precision that amazes modern scientists. The Egyptian calendar, created more than 5,000 years ago, determined the length of the year to be 365¼ days. This differs by only 11 minutes and 14 seconds from modern measurements made using atomic clocks. The temple at Dendera contains a star map depicting constellations with the accuracy of modern astronomical catalogs. The positions of the stars correspond to their location in the sky 4,000 years ago, taking into account the precession of the Earth's axis. Calculating precession requires observations over thousands of years and complex mathematical calculations. Egyptian priests predicted solar and lunar eclipses with minute precision. The Carlsberg Papyrus contains tables of eclipses for a period of several centuries ahead. Modern verification has shown that of the 120 predicted eclipses, 117 occurred at the specified time with an error of less than an hour. The orientation of the pyramids of Giza corresponds exactly to the positions of the stars in the Orion constellation at the time of their construction. The southern shaft of the king's chamber is directed toward the star Alnitak with an accuracy of angular minutes. The northern shaft points to the North Star of the Old Kingdom era, Alpha Draconis. Egyptian astronomers knew that the Earth was spherical 2,000 years before this fact was officially recognized in Europe. The calculations of the size of the globe contained in the temple texts differ from modern data by less than 3%. This requires measuring the length of the meridian arc using methods similar to those used by Eratosthenes. The calendar of the temple at Edfu takes into account the precession of the equinoxes, the slow shift of the vernal equinox relative to the stars. The complete cycle of precession is 25,776 years, which corresponds exactly to modern astronomical data. Knowledge of precession requires continuous observation over thousands of years. Egyptian priests compiled tables of planetary movements with sufficient accuracy to predict their positions decades in advance. A papyrus from Abusir contains ephemerides of the planet Venus for a period of 8 years. Modern verification has shown an error of less than 1 degree in determining the planet's position. The Karnak temple is oriented so that on the day of the winter solstice, the sun's rays penetrate through the entire enfilade of halls and illuminate the sanctuary deep inside the temple. The optical path is more than 100 meters long, and the orientation accuracy does not exceed angular minutes. This requires knowledge of the exact date of the solstice and consideration of refraction in the atmosphere. The star clocks of Egyptian temples showed the time with an accuracy of 1/4 of an hour. The principle of operation is based on observing the culmination of certain stars at different times of the year. Star timetables contain corrections for the geographical latitude of the observation site and the time of year. Egyptian astronomers knew the periods of the planet's revolutions around the Sun. The sidereal period of Mars, indicated in temple texts, is 686.5 days, which differs from the modern value by less than half a day. Determining the periods of the planets requires many years of observation and complex calculations. The lunar calendar of ancient Egypt took into account the uneven movement of the moon in its orbit. The length of the lunar months varied from 29 to 30 days, depending on the speed of the moon. Modern celestial mechanics explains these variations by the elliptical nature of the moon's orbit and the influence of the sun's gravitational pull. The astronomical knowledge of the ancient Egyptians testifies to the existence of a developed scientific school that possessed accurate observation instruments and mathematical methods of data processing. The chemical technologies of ancient Egypt included complex processes that modern science long considered inaccessible to ancient civilizations. The mummification process required a deep knowledge of the biochemistry of tissue decomposition and the use of chemicals with antiseptic properties. Analysis of mummies has revealed the use of more than 40 different chemical compounds. Natron, the main substance used for mummification, is a complex mixture of sodium carbonate and sodium bicarbonate, with the addition of sodium chloride and sodium sulfate. The Egyptians extracted natron in certain areas and purified it to obtain compounds with the desired properties. Modern analysis has shown that ancient chemists knew exactly the optimal proportions of the components. Embalming resins contained terpenes, phenols, and other organic compounds with pronounced antibacterial properties. Egyptian craftsmen created compositions from resins of various plants, achieving a synergistic effect, enhancing the preservative properties when used together. This approach requires an understanding of the chemical interactions between substances. Egyptian dyes demonstrate mastery of complex organic synthesis technologies. Egyptian blue, the first artificial pigment in human history, was obtained by heating a mixture of sand, malachite, and natron at a temperature of about 1,000 degrees Celsius. The chemical formula of the pigment, copper and calcium silicate, was only determined in the 20th century. The production of papyrus required knowledge of the chemical processes involved in processing plant fibers. Papyrus stems were soaked in solutions containing alkalis and organic acids, which destroyed the lignin and strengthened the cellulose fibers. The resulting material was superior to many modern types of paper in terms of strength and durability. Egyptian glassmakers created colored glass using metal oxides as dyes. Blue cobalt glass contains less than 1% cobalt oxide, requiring precise dosing and an understanding of how small additions affect the properties of the material. The technology for producing cobalt glass was lost in the Middle Ages. Analysis of Egyptian cosmetics has revealed the use of lead, antimony, and other metals in the form of finely dispersed powders. The particle size did not exceed 1 micrometer, which requires special grinding and classification methods. Modern technologies for producing nanoparticles are based on similar principles. Egyptian metallurgists used fluxes, chemical substances that lower the melting point of ores and improve the separation of metal from impurities. The composition of fluxes included borax, potash, and other compounds in strictly defined proportions. Incorrect dosing could lead to metal loss or poor quality alloys. The leather tanning process required the use of tannins, complex organic compounds that bind with skin proteins and give it strength and elasticity. Egyptian tanners obtained tannins from acacia bark, mimosa fruits, and other plants, creating compositions with specific properties. Egyptian perfumers possessed technologies for extracting aromatic substances from plants using distillation and enfleurage methods. Essential oils were obtained by steam distillation, a method that was officially invented by Arab alchemists in the Middle Ages. Analysis of residues in ancient vessels confirmed the use of these technologies 4,000 years ago. Egyptian pharmacists created medicines by extracting active substances from plants. The Ebers papyrus contains recipes for tinctures based on ethyl alcohol obtained by fermenting grain. The alcohol concentration in some preparations reached 40%, which requires knowledge of distillation and rectification processes. Preservatives for food products included organic acid salts, natural antioxidants, and plant-based antiseptics. Egyptian bakers added substances to dough to prevent mold growth and extend the shelf life of bread. Modern analysis has confirmed the effectiveness of these additives. The technology for manufacturing faience required precise control of the chemical composition and temperature regime. Egyptian faience consisted of quartz sand covered with a thin layer of vitreous glaze. The firing temperature had to ensure that the quartz sintered without deforming the product, a technological window of several tens of degrees. Egyptian chemists knew the properties of acids and alkalis and used them to etch metals and process stone. Hydrochloric acid was obtained by heating table salt with clay, and sulfuric acid was obtained by burning pyrite. The concentration of acids was controlled by their effect on various materials. The chemical knowledge of the ancient Egyptians covered a wide range of processes and materials, demonstrating a systematic approach to studying the properties of substances and their interactions. The building mortars of ancient Egypt surpass many modern building materials in their characteristics. Analysis of the mortar used in the construction of the Pyramid of Cheops revealed a unique composition that provides strength exceeding that of the limestone blocks themselves. After 4,500 years of exposure to the desert climate, the mortar retained its properties. The basis of the Egyptian mortar was high-purity gypsum, mixed with finely dispersed quartz sand and organic additives. The sand particles were no larger than 100 micrometers, which ensured dense packing and minimal porosity. Modern building mortars have significantly higher porosity and, accordingly, lower strength. Organic additives in Egyptian mortar included proteins, polysaccharides, and other biopolymers, which acted as plasticizers and strengthening agents. Milk casein gave the mortar elasticity, while egg albumin improved adhesion to stone. These natural additives are as effective as modern chemical plasticizers. The thickness of the joints between the pyramid blocks ranges from 0.5 millimeter to 2 millimeters. At the same time, the mortar is evenly distributed over the entire contact area, which requires low viscosity at the time of laying and rapid setting under load. Modern quick-setting mortars do not provide such uniform distribution. The bond strength of Egyptian mortar with limestone exceeds the strength of the stone itself. When the blocks are destroyed, the cracks pass through the stone, not along the joint. This means that the mortar forms a single structure with the stone at the molecular level. Achieving this effect requires the chemical composition of the mortar and stone to be exactly the same. In the underground chambers of the pyramids, where the air humidity reaches 90%, the mortars have retained their properties without any signs of degradation. Modern cement mortars in similar conditions disintegrate within a few decades due to corrosion of the reinforcement and leaching of the binder. Analysis of solutions from various Egyptian monuments has shown that their composition was adapted to local operating conditions. In areas with high humidity, hydrophobic additives were used, and in seismically active zones, plasticizers were used to increase resistance to deformation. Egyptian builders used mortars for various purposes. Masonry mortars for joining blocks, leveling mortars for creating perfectly flat surfaces, and decorative mortars for finishing work. Each type of mortar had an optimized composition to ensure the required performance characteristics. The setting time of Egyptian mortar ranged from 15 minutes to 2 hours, depending on the composition and conditions of use. This allowed builders to adjust the position of the blocks after laying, but ensured sufficiently rapid hardening to continue work. Modern mortars rarely offer such flexibility of use. The color range of Egyptian mortars included white, yellow, red, and black, obtained by adding mineral pigments. Colored mortars were used not only for decorative purposes, but also to code different types of masonry. This facilitated quality control of construction work. Egyptian craftsmen mastered the technology of creating waterproof mortars for lining reservoirs and canals. These mortars contained bitumen, resins, and other hydrophobic additives. Their waterproof properties remained intact for centuries without the need for repair. Solutions for restoration work had a composition as close as possible to the material of the structure being repaired. This ensured the compatibility of materials in terms of thermal expansion coefficients and elasticity modules. Modern restoration practice is based on the same principles. The technology for making mortars was passed down from master to apprentice and kept strictly secret. Each construction guild had its own recipes, adapted to specific conditions and types of structures. After the fall of Egyptian civilization, many secrets were lost forever. The building mortars of ancient Egypt represent the pinnacle of ancient construction chemistry, demonstrating a deep understanding of the properties of materials and their interactions. Water technology in ancient Egypt included complex engineering systems that provided irrigation, water supply, and drainage throughout the country. The irrigation system of the Nile Delta consisted of thousands of canals with a total length of over 100,000 kilometers. Managing such a complex system required precise hydraulic calculations and coordination of the work of numerous water control structures. The canals had a trapezoidal cross-section with optimal slope angles to minimize erosion and maximize flow capacity. The slopes of the canals were calculated with an accuracy of centimeters per kilometer of length. Modern hydraulics uses the same principles for designing irrigation systems. Egyptian engineers created a system of sluices to regulate the water level in the canals. The design of the sluices allowed for precise control of the water supply to the irrigated fields. The mechanisms for raising the sluice gates worked on the principle of a lever and counterweight, ensuring smooth regulation of the water flow. Water lifting devices known as shaduffs were used to lift water from wells and canals to a height of up to 5 meters. The design of the shaduff is based on the principle of a lever with a variable arm, which allowed one person to lift loads weighing up to 100 kilograms. The efficiency of such devices reached 80%. Archimedes' screw, used for lifting water, was invented in Egypt long before Archimedes. Egyptian screws had an optimal spiral geometry, ensuring maximum performance with minimum energy consumption. Modern screw pumps operate on the same principles. The water supply system of the city of Memphis included underground water pipes made of ceramic pipes up to 30 centimeters in diameter. The pipes were connected by couplings with resin and fabric seals. The working pressure in the system reached 3 atmospheres, which required high-quality pipes and joints. Egyptian hydraulic engineers knew how to purify water using filters made of sand, charcoal, and other materials. The multi-stage purification system included sedimentation tanks, sand filters, and charcoal adsorbers. The quality of the purified water met modern sanitary standards. The drainage systems of Egyptian cities prevented waterlogging and the spread of disease. Underground collectors carried rainwater and sewage outside the cities. Pipe slopes were calculated to ensure self-flowing water without stagnant areas. The hydraulic calculations of Egyptian engineers took into account pressure losses due to friction, local resistance, and other factors affecting the movement of water in pipelines. Nomograms for hydraulic calculations found in temple archives are as accurate as modern engineering reference books. Water clocks, or clepsydras, were used to measure time with an accuracy of 1/4 of an hour. The principle of operation is based on the constant speed of water flowing through a calibrated opening. The shape of the vessel was calculated to compensate for pressure changes as the water level decreased. Egyptian engineers knew the law of communicating vessels and used it to create water levels, prototypes of modern levels. Such devices made it possible to determine the differences between distant points with an accuracy of several centimeters. Animal-powered irrigation machines lifted water to a height of up to 10 meters. The design included a gear system that increased torque and allowed the pulling power of oxen or horses to be used efficiently. The capacity of such machines reached 100 cubic meters of water per hour. Waterproofing of Egyptian structures was carried out using bitumen, resins, and other waterproof materials. Multi-layer waterproofing systems protected underground rooms from groundwater for thousands of years. Modern waterproofing materials are based on similar principles. The water technologies of ancient Egypt demonstrate a deep understanding of the laws of hydraulics and a high level of engineering skill in the field of water management. Textile technology in ancient Egypt reached a level that modern industry has only surpassed with the advent of synthetic fibers. Linen fabrics from the tombs of the pharaohs have a weave density of up to 500 threads per square centimeter. For comparison, modern high-quality cotton fabrics have a density of no more than 300 threads per square centimeter. The fineness of Egyptian linen reached incredible values. The thickness of the threads was less than 50 micrometers. This corresponds to yarn number 300 in the modern classification. The production of such fine yarn requires special fiber processing and spinning technologies under controlled temperature and humidity conditions. Analysis of fabrics from Tutankhamun's tomb showed the use of mercerization technology, the treatment of cotton fibers with alkaline solutions to give them shine and strength. This technology was officially invented by John Mercer in 1850, but Egyptian craftsmen had been using it for 3,000 years before that. Dyes for fabrics were obtained from plants, minerals, and animals using complex chemical processes. Royal purple was extracted from mollusk shells using enzymatic reactions. 10,000 shells had to be processed to obtain 1 gram of dye. Color fastness was ensured by mordants, chemical compounds that form strong bonds between the dye and the fiber. Egyptian weavers mastered the technique of creating patterned fabrics, using up to 20 different colored threads. The complexity of the patterns required the use of programmable looms, prototypes of modern jacquard machines. Perforated bone plates determined the sequence in which the warp threads were raised. The water-repellent properties of some Egyptian fabrics were achieved by impregnating them with waxes and resins. Analysis has shown the use of compositions of beeswax, vegetable resins, and animal fats. The treated fabrics retained their hydrophobic properties for thousands of years. The felting technology allowed the creation of dense materials from sheep's wool without the use of looms. Egyptian felters controlled the felting process using hot alkaline solutions and mechanical action. The density of the finished felt reached 1 gram per cubic centimeter. Egyptian tailors used patterns cut from papyrus to cut fabrics. The complexity of some patterns indicates knowledge of the principles of unfolding three-dimensional surfaces onto a plane. The clothes of the pharaohs had an anatomical cut, ensuring a perfect fit. Embroidery threads were made of gold and silver, less than 1/100th of a millimeter thick. Metal threads were wound onto a silk base in a spiral with a pitch of less than a millimeter. This technology requires precision equipment and highly skilled craftsmen. The fabrics in the tombs were preserved using special chemical compounds that prevented the decomposition of organic fibers. The preservatives included natural antioxidants, antiseptics, and color stabilizers. The effectiveness of these compounds is confirmed by the excellent condition of the fabrics after thousands of years of storage. Ropes and cables made from plant fibers were produced using a technology that twisted the threads at an angle to ensure maximum strength. The cables used to build the pyramids could withstand loads of up to 10 tons with a diameter of 50 millimeters. Modern synthetic cables have similar strength characteristics. Egyptian craftsmen knew how to obtain artificial fibers from plant cellulose. Papyrus fiber, extracted from papyrus stems by chemical means, resembles modern viscose in its properties. The production process included treatment with alkalis, acids, and enzymes. Fabrics were bleached using sunlight and chemical reagents. The fabrics were soaked in soda solutions and left in the sun for several weeks. The bleaching effect was achieved through photochemical reactions that destroyed the natural dyes in the fibers. The technology of dyeing fabrics in several colors with clear boundaries between the areas required the use of resists, substances that prevent the dye from penetrating into certain areas of the fabric. Waxes, resins, and proteins were used as resists, forming protective films on the surface of the fibers. The textile technologies of ancient Egypt represent the pinnacle of ancient craftsmanship, demonstrating a deep understanding of the properties of fibers and mastery of the complex chemical processes involved in their processing. The acoustic properties of Egyptian pyramids and temples demonstrate a deep understanding of the laws of sound propagation and their practical application in architecture. The king's chamber in the Pyramid of Cheops has a reverberation time of 8 seconds, which is optimal for musical performances. Modern concert halls are designed with similar acoustic characteristics. Frequency analysis of the acoustic properties of the pyramid showed the presence of resonance frequencies in the range from 20 to 100 Hz. These frequencies correspond to the fundamental tones of the human voice and many musical instruments. When sounds of certain frequencies are reproduced in the king's chamber, the amplitude is amplified several times. The granite sarcophagus in the king's chamber is tuned to a frequency of 440 Hz, the note A of the first octave of the modern musical scale. When struck on the edge, the sarcophagus emits a pure tone of this frequency with a duration of more than a minute. Such precision in tuning requires knowledge of the mathematical relationships between the dimensions of the resonator and its frequency characteristics. The pyramid system of corridors acts as a complex acoustic filter, changing the spectral composition of sounds. Low-frequency vibrations pass unimpeded through the entire pyramid, while high frequencies are absorbed or reflected. This effect was used to transmit certain types of sound signals over long distances. In the Karnak temple, the colonnade of the hypostyle hall creates unique acoustic conditions. A whisper spoken at one column can be heard clearly at a distance of 100 meters on the opposite wall. The effect is achieved by the cylindrical shape of the columns, which focus the sound waves. The temple at Edfu contains rooms with different acoustic characteristics for various religious ceremonies. The sanctuary has a short reverberation time for reciting prayers, while the main hall is designed for polyphonic singing. The transition between rooms is accompanied by a smooth change in acoustic properties. The pyramidal shape of the structures creates an acoustic levitation effect, the concentration of sound energy at certain points in space. When a sound of a certain frequency is reproduced at the apex of the pyramid, the effect of light objects rising due to acoustic pressure is observed. Modern science uses similar principles in technologies for contactless manipulation of objects. Obelisks functioned as giant tuning forks, resonating at certain frequencies when exposed to wind. The height and proportions of the obelisks were calculated to ensure resonance at frequencies corresponding to human hearing. In windy weather, the obelisks emitted melodious sounds that could be heard several kilometers away. The underground chambers in Serapeum have acoustic properties characteristic of soundproof rooms. The reverberation time is close to zero, creating a dead acoustic effect. Such conditions were used for meditation and rituals requiring complete concentration. The architectural elements of Egyptian temples functioned as acoustic deflectors, directing sound to specific areas. The sloping surfaces of the walls and ceilings were calculated using the laws of geometric acoustics to ensure even sound distribution throughout the room. Egyptian priests used acoustic effects to create a mystical atmosphere during religious ceremonies. Hidden resonators in the walls of temples amplified certain tones of the human voice, creating the impression of the presence of supernatural forces. Modern stage acoustics is based on similar principles. The musical instruments of the ancient Egyptians were tuned in accordance with the acoustic characteristics of temples and pyramids. Flutes and harps had a tuning corresponding to the resonance frequencies of architectural structures. This ensured maximum amplification of the music and created a surround sound effect. The acoustic calculations of Egyptian architects took into account not only the geometric parameters of the rooms, but also the properties of the building materials. The sound absorption coefficients of different types of stone were used to adjust the reverberation time and frequency characteristics of the rooms. Modern research has shown that some Egyptian structures are capable of generating infrasonic vibrations, sound waves with frequencies below the threshold of human hearing. These vibrations can affect a person's psycho-emotional state, causing feelings of awe or fear. The acoustic technologies of ancient Egypt demonstrate an understanding of the complex physical laws of sound propagation and their skillful application to create architectural masterpieces with unique acoustic characteristics. Electrical anomalies in Egyptian pyramids and temples pose questions to modern science that still have no clear answers. Measurements of the electric field inside the Pyramid of Cheops have shown the presence of a constant electric potential of up to several hundred volts between different points of the structure. The source of this potential remains unknown. The granite blocks of the king's chamber contain quartz, a mineral with piezoelectric properties. When mechanically impacted, quartz generates electrical charges, and when an electrical voltage is applied, it deforms. Millions of tons of granite in the pyramid create a giant piezoelectric generator that responds to seismic vibrations and changes in atmospheric pressure. The limestone blocks of the pyramid have dielectric properties and can function as an insulator in an electrical circuit. The alternation of conductive granite and insulating limestone layers creates a structure resembling a multi-layer capacitor. The capacity of such a capacitor can reach several microfarads. The underground chambers of the pyramid are insulated from the ground by a layer of granite several meters thick. This insulation creates conditions for the accumulation of static electricity. The low humidity in the pyramid helps to preserve electrical charges for a long time. Metal elements in the pyramid structure, including brackets and anchors, can function as electrodes. In the presence of an electrolyte, these elements form galvanic couples that generate electric current. Groundwater with dissolved salts can act as an electrolyte. The shape of the pyramid helps to concentrate the electric field at its apex. The effect is similar to that of a lightning rod. The pointed shape creates a high electric field intensity in a small volume. When critical values are reached, air ionization and corona discharge may occur. The internal chambers of the pyramid are connected by a system of shafts that can function as waveguides for the propagation of electromagnetic waves. The geometry of the shafts corresponds to waveguides for specific frequencies of the electromagnetic spectrum. This allows the pyramid to resonate at radio wave frequencies. Studies have shown the presence of magnetic anomalies in the area of the Giza pyramids. The local magnetic field deviates from normal values by several microteslas. The source of the anomalies may be the magnetization of iron-bearing minerals in granite or underground current loops. Some granite blocks of the pyramid exhibit the properties of permanent magnets. The residual magnetism of these blocks may be the result of exposure to strong magnetic fields during their formation or subsequent processing. The orientation of the magnetic moments creates a complex picture of the magnetic field inside the pyramid. Atmospheric electricity interacts with the pyramid as if it were a giant antenna. The height of the pyramid corresponds to a quarter of the wavelength for radio waves of a certain frequency. When in resonance, the pyramid can effectively receive and re-emit electromagnetic energy from the atmosphere. Experiments with pyramid models have shown the ability of these shapes to generate weak electric currents under certain conditions. The generation mechanism is related to the uneven distribution of electric charges on the surface of the pyramid under the influence of external electric fields. The conductivity of different materials of the pyramid creates a complex electrical circuit. Granite has low but non-zero conductivity. Limestone is a dielectric, and metal elements are good conductors. Such a structure can function as an electrical filter or transformer. Temperature gradients inside the pyramid can lead to thermoelectric effects. The temperature difference between different parts of the structure creates a thermoelectric voltage that can reach several millivolts. The combined effect of multiple thermocouples can create measurable electrical potentials. Some researchers suggest that the ancient Egyptians deliberately used the electrical properties of pyramids for practical purposes. Hypothetical applications include electroplating, lighting, and even wireless energy transfer. However, no direct evidence of such technologies has yet been found. Modern research into the electrical properties of Egyptian monuments continues using the most advanced instruments. Each new discovery adds to the existing questions about what knowledge of physics the ancient builders possessed. The lost knowledge of ancient Egypt is one of the greatest mysteries of human history. How could a highly developed civilization, possessing technologies that modern science has only been able to reconstruct in the last few centuries, disappear almost without a trace? Analysis of historical processes shows that the loss of knowledge occurred gradually over several millennia. The system of knowledge transfer in ancient Egypt was based on the priesthood, which jealously guarded its secrets. Technical knowledge was passed down orally from teacher to student within narrow professional castes. Written sources contained only general principles, while the details of technology were kept strictly secret. This conservatism, which ensured the stability of civilization, also made the knowledge system fragile. The political upheavals of the decline of the Old Kingdom led to the destruction of the traditional education system. Civil wars, foreign invasions, and social revolutions interrupted the chains of knowledge transmission. Many temple schools were closed, libraries were looted, and knowledge-bearers died or scattered to different regions. The Library of Alexandria, which contained about 700,000 scrolls, was the largest repository of ancient knowledge. Its gradual destruction as a result of fires, religious conflicts, and political changes lasted several centuries. The final blow to the ancient heritage was dealt by the Arab conquest in the 7th century AD. The Christianization of Egypt in the 4th century led to the deliberate destruction of pagan temples and their libraries. The new religion regarded ancient knowledge as a manifestation of paganism and demonism. Many papyri were burned, temples were destroyed, and priests were persecuted. The education system was restructured in accordance with Christian dogma. Climate change in the late period of Egyptian history led to the drying up of regions where craft production centers were located. Workshops were abandoned, and with them, technological traditions disappeared. Papyrus, stored in unfavorable conditions, was destroyed by sand, moisture, and temperature changes. The economic decline of the last pharaonic dynasties led to a reduction in funding for temples and schools. Complex technologies required significant resources to maintain, and in their absence, production methods were simplified. Gradually, the skills of manufacturing high-quality products were lost, and the secrets of craftsmanship fell into oblivion. The conquest of Egypt by the Persians, Greeks, and Romans brought new technologies, but at the same time destroyed local traditions. The conquerors were interested in exploiting Egyptian resources, but not in preserving local knowledge. Cultural assimilation took place, resulting in Egyptian technologies mixing with foreign ones and losing their specificity. The loss of writing played a critical role in the disappearance of Egyptian knowledge. Hieroglyphic writing was difficult to learn and required many years of training. With the fall of the priestly class, there was no one left to teach hieroglyphics. The last known hieroglyphic inscriptions date back to the 4th century AD. Without writing, knowledge could not be passed on to future generations. Changes in the material basis of civilization also contributed to the loss of technology. The Iron Age brought new materials and processing methods that replaced traditional Egyptian technologies. Bronze tools gave way to iron, but the secrets of obtaining special bronze alloys were lost. New technologies were easier to master, but less sophisticated in a number of respects. Social changes in late antiquity destroyed the caste system, within which professional knowledge was preserved. Craft dynasties, which had passed on the secrets of their craft from generation to generation for thousands of years, disappeared under the influence of new social relations. Knowledge that was not recorded in writing disappeared along with its bearers. Modern attempts to reconstruct ancient technologies are hampered by the fragmentary nature of the sources. Archaeological finds provide an idea of the end results, but not of the processes by which they were obtained. Ancient texts contain general descriptions but lack technical details. Experimental archaeology allows us to recreate individual technologies, but the complete restoration of ancient knowledge remains an unattainable goal. The paradox is that some Egyptian technologies still surpass their modern counterparts. Construction mortars that retain their properties for millennia, dyes that do not fade in the sun, metal products that are not subject to corrosion. All this testifies to the depth of lost knowledge. Studying the reasons for the disappearance of ancient technologies is important for modern civilization. The fragility of knowledge systems, dependence on a narrow circle of specialists, and the lack of written records of technologies are problems that are still relevant today. The history of ancient Egypt serves as a warning about how easily even the most outstanding achievements of human genius can be lost. Modern digital information storage technologies create an illusion of reliability, but history shows that any knowledge preservation system has its vulnerabilities. Only a comprehensive approach, including multiple duplication, various media, and active knowledge transfer, can ensure its preservation for future generations.